Up to this point, we have focused primarily on translation along a straight line. However, we all know motion often happens in more than one spatial dimension, so we need to learn to handle these situations. We'll start by revisiting our earlier discussion of vectors in 1D and expand that to discuss vectors in 2 and 3 dimensions. Much of what we discussed earlier about representing vectors applies, regardless of the number of spatial dimensions. We use the same symbolic representation for the vector as well as its magnitude and its direction specified by the unit vector. In more than 1D, we may still draw arrows to represent vectors, where the arrow's length represents the vector's magnitude and the arrow's direction is represented by the direction that the arrow points. Like in 1D, we have the freedom to draw the arrow where we like and still represent the vector properly. However, we need to make sure we don't stretch, shrink, or rotate the arrow. Multiplication and division of a vector by a scalar still works the same way. If the scalar is positive, the result is a new vector that points in the same direction. If the scalar is negative, then the result is a new vector that is flipped. If the scalar is dimensionless, then the new vector has the same physical dimensions, but possibly stretched or shortened or flipped as compared with the original vector. If the scalar has dimensions, the new vector is a different physical quantity. In 1D, all vectors must be aligned or anti-aligned. In more than 1D, this is no longer true. So math operations like vector subtraction and vector addition using arrows might look a bit different. However, the procedures for addition and subtraction are the same in all spatial dimensions. And we can see this once we practice a bit. So, when we use arrows to represent adding vector physical quantities, where of course all the vectors must have the same units, we still do that by, first, starting with the arrow representing one of the vectors, then moving the arrow for the other vector we are adding without stretching, shrinking, or rotating, so that the tail of this arrow is placed on the top of the tip of the first arrow, then drawing a new arrow starting from the tail of the first arrow to the tip of the final arrow. We can use the same process to represent the addition of any number of vectors in any order. To represent vector subtraction with arrows, say for example subtracting R1 from R2, we first place the arrows such that the tails of both arrows are at the same location. Then we draw a new arrow here from the tip of R1 to the tip of R2. This arrow represents the subtraction R2 minus R1. As before, we can still think of vector subtraction by converting this to a vector addition problem. And also, as before, the order matters. R1 minus R2 is not the same as R2 minus R1. In more than one dimension, vectors represented by components have more than one non-zero component. The vector operations using components work just as we described before, except that we need to perform these operations on more than one non-zero component. Also, as we discussed earlier, the component representation of a vector depends on the choice of coordinate system. So, if the coordinate system changes, then in general, the component representation changes. For a given choice of coordinate system, let's try to visualize what the components mean in more than 1D. Briefly stated, the component describes the projection of the vector along a given axis. If we use an arrow to represent the vector, we can picture this projection as the shadow cast by the arrow along a given axis.
More precisely, if we pass lines that are perpendicular to the axis through both the tip and the tail of the arrow, then the magnitude of the component describes the magnitude of the projection, while the sign of the component and the axis unit vector together describe the direction of the projection.
We can visualize projections along all three axes at once best by moving the arrow representing the vector to the origin, to place the tail of the vector of the arrow at the origin, as we show here for a different vector. We can use the same picture to visualize how to find the magnitude of a vector from the components using the Pythagorean theorem in 3 dimensions.
This also works for 1 and 2 dimensions, where one or more of the components will be 0.
Now let's emphasize that the magnitude of a vector is independent of the coordinate system. So even if we change coordinate systems, and therefore the components of the vector will typically change, applying the Pythagorean theorem to the new components will still yield the same magnitude. Now that we know how to compute the magnitude of a vector from its components, we can compute the unit vector corresponding to that same vector. Let's give this a try with this example. Here is the result, where we first compute the magnitude of the vector v, then divide the vector v by its magnitude to get the unit vector v hat. You may be surprised to find that, in general, the unit vector in component form doesn't need to have 1's as components. What must be true is the unit vector in all cases must have a magnitude of 1 with no dimensions. You can apply the Pythagorean theorem to this unit vector and verify that, in fact, the magnitude is 1. Specifying directions with angles is useful for vectors in more than one dimension. For this, we need to know and to refresh our memory about trigonometric functions. Let's again represent a vector with an arrow, and for convenience, place the tail of the arrow at the origin. We see that a triangle can be formed when we visualize projecting that vector, that arrow, along one of the axes.
If we take the magnitude of the vector as the hypotenuse and the projection as one of the legs, then the cosine of the angle between them, the adjacent angle, is given by the ratio of the component to the magnitude of the vector, as long as we make sure the angle is measured from the positive direction of the axis. If we use the correct angle measured from the positive direction of the appropriate axis, this relationship works for all coordinate axes.
Now in 2 dimensions, we can think of this in terms of a single angle, where we use the appropriate trig function to relate the vector's magnitude to projections along each axis. Here, I find it helpful to work with angles that are less than or equal to 90 degrees and use trig to relate the magnitude of the vector to the magnitude of the components, and then use the sketch to determine the sign of the components. Let's try this on this example. It's helpful to draw a sketch here, where we show vector A making an angle of 80 degrees measured counterclockwise from the negative x-axis. With this sketch, we see that both the x and y components of A must be negative. Now, we're also told here in this problem that the magnitude of A is 6 with no units. So we can form a right triangle with the hypotenuse equal to the magnitude of A. And we can take the magnitudes of AX and AY as, respectively, the adjacent and opposite legs of the triangle for the angle shown. Do a little trig and we find the magnitudes of AX and AY. And that, combined with our knowledge that AX and AY, respectively the X and Y components of A, are both negative. We get that from the figure, and that allows us to write the vector A in component form as shown.